Let's get started, everyone. Welcome back. So today we're going to be talking about streaming algorithms. This is going to be a new section on the class. We'll specifically be talking about basics of frequent items and so random sampling and quantiles today. So let's see. So I have two lectures scheduled on streaming algorithms. So it'll be a fairly brief section, although we will look at matrix sketching after the break as well. This will be kind of streaming algorithms for things like dimensionality reduction. And so it'll make sense to talk about that after we've defined the basics of dimensionality reduction. It's possible I would talk about streaming algorithms for graphs at the end of the class. I haven't figured out what to do with this last lecture yet. So if people seem to really like this, maybe I'll talk about that, or I could fill something else in there. So as we get there. So I'll define what streaming algorithms are and the space of things. It's kind of a neat area of data mining that is really focused on large data problems. And it's kind of this, it might sound like kind of a, so kind of a limited paradigm, but people started studying this way of phrasing the problems, and the techniques from this area got deployed and developed into lots of other areas. So kind of it gives kind of really simple way of formulating the basic version of lots of problems that show up elsewhere. There's a lot of things we could cover in this space, and I will pick out my favorite. Things that I think are not too complicated. So I like them because I like things that are simple and useful and actually work. And so those are the things that I'll talk about. The next homework will be on frequency estimation. I haven't posted this yet. Maybe by the end of the week, maybe early next week. It's not due till after break. I'm hoping it'll be kind of a little bit shorter than some of the other homeworks. Hopefully the homeworks mostly have not been too time consuming, or have they been kind of so how do you think this class compares to other classes at this level? And are the homeworks more time consuming or less time consuming? Okay, who thinks more time consuming? Thinks less? Yeah, okay. Hopefully you still feel you're learning something from them? Yeah, okay. If you want like more work, I can give you more work. No, okay, good. I just like this concludes the intermediate student feedback section of the class. Okay. Feel free to send the other anonymous feedback or in person as well. Okay. And then what was I going to say about the midterm on Wednesday next week? Let me just reiterate a few things I said before. It will be in class. Okay, so you have to be here. Expect a few more people. So it'll be a little bit more crowded. Try not to sit directly next to someone. I'll try and space you out. I'm not sure if we'll all fit every other seat. I think it'll be, but it should be close. Okay. It will be probably slightly longer, but hopefully not harder than the midterm practice test. Okay. And the other important thing is it will cover everything up until the test. So the streaming algorithms is possibly on there. And you will be allowed to bring in one sheet of paper, front and back, an 8.5 by 11. Don't bring in a poster. And you will be able to use that as reference. So I think this is a useful way to study. Think about what you can put on one sheet of paper. It's a good way to study for the exam, and then you won't have to kind of memorize things. If you think there's some really details of some formula or something that you want to write down, you can write down on the piece of paper. You will not be allowed computers or calculators or using like AI through an earpiece. Please don't. So try and do that. And I assume if you look at the practice exam, hopefully shouldn't like that. You shouldn't. I don't think you'll have trouble finishing within the 80 minutes we have in in class. Okay, I assume some people will take until the very end, but most of you will probably finish. My aim is maybe halfway through the class is when I'll start seeing the bulk of people finish. And some people want to double check everything, and that's that's totally fine. Okay, that's my intention. You know, we'll see how it goes. But we'll try and make sure it goes smoothly. Okay. Okay, next class, I want to talk about the intermediate report, which will be due after break. You should be getting data collection feedback. Pretty much everything seemed fine on the data collection report. The TA may have sent one or two groups a little bit of feedback there. Intermediate report, I will want a bit more information at that point. I want to see some progress, enough to know if you're on the right track and get feedback. You will have to have a report that will be 1 page per member of the group. So if you have 2 members of the group, it's 2 pages. Progress on what you've done so far. It should be self-contained. We're going to use half of this class. You're going to pair up or triple up some groups, and you're going to share and get feedback from others. So you're going to hand the report to other people in the class. Okay, and then later this week, you're going to schedule time to meet with me and get some feedback from the class. Every group will need to meet with me for like, you'll get like 10 minutes. And so we'll get some feedback on that. If you want more time than that, I'm available before and after class and office hours and stuff. Okay, so you'll want to have some progress. If you're doing things already, then it might be enough, but enough so I can give you feedback and say you're on the right track, or you should change this in order to kind of things to turn out well. Okay. Okay, so I'll talk a little bit more about that, but at the beginning of Monday's class. And then we'll send out some announcements over Canvas as well. All right, this all seems good. All right. Okay, let's talk about streaming algorithms. So the kind of the theme of this section of the class is your data is so is big, okay? And in fact, by what do I mean by big? I mean it's too big to fit on so you're like too big to fit in your computer, or just like in memory. Okay, so maybe you've got a very large hard drive, but to fit it all in memory, if you try and load it all in memory and load up an application that expects it in memory, it's going to start thrashing, right? So if you experience kind of thrashing with too big of a data set where the application gets really slow because you're trying to load this in memory, what happens is it might be stored on disk, and things you can do random access on things which are in your memory, but if something's on disk, it takes a long time to go and get, right? The other way of people thought about this is, say you're a computer that's like sitting on a router, like the internet, okay? Then there's all these packets of data streaming by, and the router's job is not to store everything, but is to send the packet on its way. And so there's very limited compute and storage at the router compared to the amount of data which is streaming through it, right? And so this is kind of the challenge. And there are kind of 3 basic ways people have thought about how to deal with large data. Okay, and we'll The first one is the first one would be so parallelism. Okay, so instead of solving your questions, your data mining questions all in one computer, you go and get more computers. Okay, so it only helps to use more computers if you're a little bit smart about how you can spread out the computation between them. We're not going to talk too much about parallelism in this class. There are specific classes in our department that talk more about how to design algorithms which run in parallel. There used to be a section in this class or lecture to on MapReduce, which 10 years ago was kind of the coolest thing. It was like what these chatbots are now. It was like figured out how to make doing parallelism very easy, especially for tasks in data mining. And so it was a way to set up a small number of operations you can consider. And if you did those, if you implemented those, then they would do all the parallelism under the hood. Okay, we're probably not going to talk about this unless I get requests, then we can do this for the last lecture. Okay, the second way of dealing with stuff would be would be sampling. Okay, so the idea is that you have some very large X, which is my the data, and I'm going to sample S from the dataset X, right? So S will be S1, S2 up to Sn. Okay, and the full size data is maybe like some uppercase n. So n is going to be much less than the size of the data. And I hope that the random sample I've drawn from the data set is representative of the full data set. Okay, and we talked about the beginning of the semester these assumption that the data was IID. This kind of underlies basically all of supervised machine learning. That the assumption is your data is ID allows you to do things like cross-validation and stochastic gradient descent. These are necessary assumption for those models to really make sense. So any sort of pattern you can learn under this assumption, well, you can approximate with sampling. And so then the question is, how many samples do I need in order to approximate the phenomena, right? And this is a very well-studied question. It ties into statistics, and there's a lot of big questions. How many samples do I need? I will touch on this in the lecture today. This is kind of a fairly in many settings where we want to make some sort of informed inference from data. It makes sense that sampling would be a approach. And it turns out what I think is interesting is that you can often do better than sampling, right? So if I have my huge data, again, if it doesn't fit on my computer in memory, I draw a sample. Hopefully the sample fits in memory, and then I can run some algorithms on the sample. Then this third approach I will call streaming, and it's grown into something more than this, but this will be the model we say today. And so here we'll think of our X is our very large data, but there's going to be some sort of some order to X. And so I've written the pointy brackets to describe that there's an order. So xi ... xn. Okay, so that there's an order at which these items are stored or are presented, and I want to somehow compute on them. But the idea is that, like I'm sitting on a router, I get to see them once and then they are off on their way. I can't store everything. Okay, so this model allows me to read each xi once, but not store. So I can't store all. I can maintain okay, a small space. So summary of the data. So I want to somehow think of reading the data in the order they're given. Okay, they may be representative, maybe the IID assumption holds, but I'm not able to control the order. They're given to me in some order. I need to read the item once, maintain some sort of summary of the data I've seen, and then the items are gone. I can't store all. Maybe I can store a small number of them, but not all of them. And so the goal here has really been kind of to optimize this small space of the summary that I'm maintaining on this data. Okay, so think of like if you're computing statistics, you've heard of the sufficient statistics of the data. Well, if you have a model of statistics, the sufficient statistics tell you what the choice of the model was. So maybe I just need to maintain the sufficient statistics or the parameters of the model. Then that would be enough, but can I store and update these, right? So can I maintain these as I'm reading the data just once? And maybe I don't even know how long the data is going to be. It's like in a router, more data just keeps coming, right? Or I'm one of these internet scale companies. They have some sort of web page. People keep coming to Google and making searches. It never stops. They hope it never stops. Same way people keep coming to Amazon and looking at and ordering new products. This just keeps coming. I want to maintain some statistics on all the data I have. Maybe not store all the interactions or everything about them, but maintain some sort of summary of this. This is also useful if you're in the setting where the data fits on your hard drive, but not in the memory of your computer. What you do is you essentially are scanning the hard drive once, reading all the data, and maintaining a summary of it. And I only want to scan it once, bring it in and out of memory once. Then I don't. Your computer can somewhat prefetch stuff, and it doesn't have to thrash as it's trying to do random access on these things, right? So I only read everything once. This is still an efficient way to run kind of some algorithms. When we were talking about the min hashing algorithm, and there were two for loops, and I had the outside for loop read over the data once, right? And the inside for loops was maintaining multiple of these hash functions. That's because it makes sense to read the data only once. I only have to bring it off the hard drive once, and I can maintain a summary representation without having to keep accessing data on the hard drive over and over again. Okay, so this is it's turned into this very kind of powerful model. And the idea of how can I maintain a small space summary of the data is kind of something that's now showing up in a lot of scaling up machine learning algorithms to these very large scales of the data that you actually have to run them on. Okay, so this is kind of taking on a lot of interesting roles. Okay, so we'll talk about. Let me just think about this. Review this model again, and we'll go through an example. We'll think about our data. I'll call this A, and we'll say A1, A2, A3, up to AI, and maybe up to AN. Okay. And I'm going to say that in this example, I'm going to say each AI is going to be a real value. Okay. And then we can think of that uppercase AI is A1, A2, up to AI, right? So I can think of the stream up to this point. So I'm reading the stream from left to right, or it's coming and streaming in the router. I'm scanning the hard drive, and I'm reading it up to some point A. My data set is then A, so sub uppercase A, so sub I. Now I want to have something to be able to maintain some summary, some property of this data. So uppercase, so AI. And I'm going to talk about an example of the mean of AI. Okay, I'd like to maintain the mean of all these values, so the average, right? Remember, this is 1 over I, sum, let's say j equals 1 up to I of AI, right? So I want to maintain this quantity, right? Okay, and I can only read every data point once. Okay, so if I have stored the mean, let's say I've stored this in a value v, okay, so I have some value vi, which is the mean at point I, and I get another data point. How do I update the mean? Okay, so I'm given, let me say this again, I have stored, I have some memory here, and I've stored in it this value vi, and then there's this stream coming, A1, A2, up to AI, and now, right, I've stored up to this point, and now I'm given another point AI plus 1, and I want to do some operation that is somehow using AI plus 1 and whatever I've stored, and I want to get to VI plus 1. Yeah.
Would you multiply VI by I, add AI plus 1, divide by plus 1?
Yeah, okay, so you want me to use I, so all I'm given is a value AI. So what do I have to store in the memory? Right now I've stored VI in there, and you want me to do some operation, VI times I. So where's I stored? Yeah, okay, good. So let's put I inside the memory too. So I'm also updating. Okay, so V times I, and then
Add
plus AI plus 1, okay?
by that whole thing
Divide by I plus 1. Yeah, so this will work. This is great. Okay, there's another way I'd recommend to do it. I had to, and the key idea was I also had to store I in here. Instead, what I'm going to recommend doing, and there might be some advantages to doing it this way for numerical reasons, how you describe, but this is a little simpler to think about. I'm going to store j equals 1 to I of AI. I'm going to call this the sum. So I'm going to store the sum instead, and I'm going to store I, which is going to be equal just the number of steps. Okay, so I'm going to store this in my memory, and then I can always output VI equals SI divided by I. Okay, but the good thing is these two things are easy to update, right? So now I store this in I plus AI plus 1. Well, all I have to do to do this update here is this will be SI plus 1. SI plus 1 equals SI plus AI plus 1. And I plus 1 equals I plus 1. Okay. And so this is how I do the update. Right now, the update is more straightforward. I just add something under the sum and I update my total counter here. And then if I want to get out VI vi plus 1, this is just si plus 1 divided by my I plus 1, which I've stored explicitly right here. Okay, so by storing it, instead of just storing the sum, but I've broken it down into the sum and the total count, now I can get the mean out. And this is very easy to update. Or if I just stored the mean without the counter, right? That's something else I'd have to store. If I just stored the mean without the counter, I don't know how to update the mean. So I have to be a little bit more careful about how I store the data so it can be easily updated. Okay. Okay, what if I wanted to store the sample variance? What if I wanted to store 1 over I, j equals 1 to I, times aj minus vi, which is the mean, right? Or I can write this as the expected value of ai squared. Okay? Do you think I could? So this is the variance. This is the variance of ai. How would I do this? Now I need to maintain for each of the AJs, even the ones in the past, like A3, I need to subtract the mean off of here, which I didn't know until I got to the ith thing. I need to square it and sum all these up and divide by I. Yeah, so this is trickier. Okay, so just do the so for the variance of ai, I need to rewrite 1 over I, j equals 1 to I, of ai minus expected value of ai squared. I can rewrite this as 1 over I, j equals 1 to I of ai squared minus expected value so this is the expected value of this squared. Okay, so I can rewrite the variance in this way. This is if you remember from a probability class, you can write the variance in either of these two ways, either the expected value, which is this is equal to the expected value of ai squared minus the expected value of ai squared. Okay, so this would be a way of rewriting it. So then I can store in my memory the value I, the sum, where SI is 101, which is the sum of j equals 1 to I of ai, and then I can store the sum squared of ai squared. Okay? And now if I store these three things, each of these is easy to maintain. This is just a counter. This is just a sum, and this is the sum of all the elements squared before I add them up. Then I can recover the variance of ai is going to be qi divided by I minus si divided by I quantity squared. Okay, so this is a trick for storing the variance. Okay, and again, I have to be slightly more clever than not just the counter, but I have to store the sum and the and the sum of the squares as well. But then if I do this, I can recover and I can get the variance of all the elements in the string. Okay, yeah. Yeah, this is at the ith point in the stream, right? I'm this long stream A, and I'm at I've seen the ith thing, and it's going to keep coming, and I maintain this storage of 3 different kind of quantities, an integer to real values, and I can maintain them because each of them is just a sum of things that I've seen so far. Yeah.
Inside these summations, shouldn't the lowercase ai actually be AJ so that we're iterating?
Yes. Great. Very, thank you. A mistake that might AJ. So this is AJ quantity squared before I sum it up, and just the sum of the AJs. Great, great. Okay, good. So this is kind of a first thing you can do. The mean and the variance and things like this are things that actually in a stream I can calculate exactly. And there's this nice thing in a constant amount of space. Okay, most of streaming algorithms are when I can't maintain it exactly in a constant amount of space. The first trick we're going to use towards doing this is actually going back to the second kind of theme of parallelism, sampling, and then streaming. How do you maintain a random sample? So inside of a stream, right? So the goal here, the goal is to maintain a random sample B from A, where this guy is the stream A1, A2 up to AN. Okay, so I want to maintain a random sample, maybe a random sample of size K, right? Let's say the size of B is equal to K, and I want to maintain a random sample. If I have a random sample, as I tried to explain, and I'll give some examples of what I can do with it, but I can guarantee that I'm going to be close to the full data set on a whole bunch of different kind of tasks. That makes sense to try and kind of learn if a random sample of the data set makes sense, then it will kind of generalize well to new data from the same distribution. Okay, so and the classic way of how to do this is called reservoir sampling. Okay, so I'm going to maintain a random sample B. This is my reservoir. This is where I maintain our water at the base of the foothills. And then as we drink water during the day, more rain comes or snow melts and hopefully fills up the reservoir, right? But we want to do this with a random sample in the stream, right? So again, we're going to have A1, A2, up to A, we'll say up to AK, and up to AI, up to AN. And at every point here, there's going to be a random sample B. And then I see another point I need to, well, after that next point, maybe that next point should also be in the random sample, and I have to somehow update what I've maintained as my random sample. Okay, so again, this is an algorithm that I like because it's very simple. Okay, and there are 2 ways of thinking about, if I say a random sample of a stream, this could actually mean 2 different things, okay? There's a whole class of things that doesn't yet mean if I want to sample proportional to a weight, right? In k-means plus, some points we want to sample more likely than others. That's not what I'm talking about. Each point should be equally likely to be picked, okay? But there's still 2 versions of this, okay? One version is sampling without replacement. Okay, so that means I'm sampling a bunch of things and I might sample something twice, right? If I draw a completely IID random sample of a subset of students from the class, I close my eyes, I spin around, and I pick someone as a sample. I do it again. Third time, I may have come back and picked the first person over again. Okay, that's a sampling with replacement. Okay, what else? And you could do that by running reservoir sampling k times in parallel. Okay, it's a random algorithm. And the k times in parallel each maintains a reservoir of size 1. Okay, and it's kind of seems kind of silly to do. What we are going to do instead is we're going to maintain a reservoir of size k, but we're not going to maintain any duplicates. Okay, and this is usually a little bit better sampling. It spreads things out. If you don't have weights, this is basically always very slightly better than if you sample kind of with replacement. So you could sample someone twice. Okay. So we're going to sample. This is going to be without replacement. Okay, and this is the trickier version of it. Okay, so the algorithm, again, will be simple. Okay, I'm going to keep the first, so k items in the stream. So initially, B will be a set A1, A2, up to AK. Okay, so for the first k items, this, okay, this will be my initial B at, not at I, at point K. It's just going to maintain the first K items. I'm going to fill up my reservoir. If I have an empty spot, I'm going to put something in. Okay, so for the first K things is actually deterministic because I want them without replacement. Okay, then what's going to happen is I'm going to come to I'm going to then have a for loop and then do something different for j equals k plus 1 up to n, right? So starting after the first k things, now I need to do something more interesting because now I need to make sure it's a random and I don't have exactly one way to fulfill the random sampling more. Okay, so now this k plus 1th item, maybe I want to include this in the random sample, right? With what probability should it be in the random sample? If I just have k plus 1, let's say the first step after I filled up the reservoir for the first time, I now see item A of k plus 1. What probability should it be in the random sample? So there are k plus 1 things I keep k samples and I have k plus 1 options of things to keep. All right, so I want to keep it. What's the probability? I'm going to keep A, J in B with probability. What should the probability be? It should be, well, k out of j. All right, so there of the first j things, let's say k is 10. I'm going to keep 10 things in my reservoir. I've up to the 100th thing so far. The probability at that point, the 100th thing should be in the reservoir is 10 out of 100. So it's 1/10. All right. And if I see another thing, the 101th thing, well, then it'll be 10 out of 101. Okay, so that's the probability that thing should be kept. And so I know if I want to keep a perfect random sample of k things, I should keep it with probability k over j. Okay, but if I kept it with probability k over j, my reservoir is full. What should I do? Well, and I'm going to boot random B in B from B. So I'm going to replace, if I keep it, I'm going to replace one of the things from the reservoir at random. I'm going to, if I decide to keep it, then I'm going to go look at the reservoir, eeny, meeny, miny, mo, pick one of them at random and throw it out. Okay, which one should I have thrown out? Well, that's uniform, so they should all be equally likely to be so thrown out. Okay. So and if otherwise, if I do not keep it, then I'm going to keep the same. Okay, great. So this is the whole algorithm here. Okay, so this is the reservoir sampling algorithm. Every time I see a new item, I flip a coin, I keep it with K over J. As J gets bigger, the probability of keeping it decreases. Right, so this is, I keep getting asked, how is AI influencing your teaching? And it keeps popping up on my tablet as I'm trying to lecture. Okay. This probability is the key thing, right? So K stays the same. K is a fixed value, right? And J is increasing, right? So as I get more, I see more and more things, the probability I keep something is decreasing every time. So this gets smaller and smaller. So most of the time, I'm not going to throw anything out. I'm going to keep it the same. In fact, you can argue like over the stream, the expected number of things you kick out of it is going to be logarithmic in n. Okay, so actually only log n times, roughly, depending on k, do I need to actually eject something from the reservoir. So the gap between ejecting things on average gets larger and larger over time. And so most of the time I just keep the random sample as it is, and then when I do pick something new, I have to boot something out. And kind of the amazing thing about this is you can show that even though I'm booting them out at random, right, that at the end I can guarantee everything is in the stream in the reservoir at the right probability. Everything is in the reservoir at exactly K over N after the nth point in the stream. Yeah.
So you're building this while you're
as we're going through the stream. Yeah.
So if first K, J is going to be correlated next thing.
Yeah. So the probability I keep something changes and it keeps decreasing. And I'm maintaining a reservoir set B as I go. Yeah.
So the idea is that if we are keeping something, that's the only time we boot a random value from B.
That's correct. Yep. So most of the stream B stays the same. So it's a pretty kind of stable. The probability I actually have to do any work other than flipping a random coin is very small, right? So this step occurs less and less as I go. But at the end of the stream, I get a reservoir set B, which is kept with the right probability. Yeah.
I'm so confused what this probability is, K over J.
Yeah, so K is the number of things I'm keeping overall. So let's say I want what? The size of the set B. And J is the jth point in the stream. I'm sliding this across the stream, and initially I'm at the 10th spot, and then I get to the 50th spot, the 200th spot, 50, 200, those are the value J. So at the 200th spot, if I'm keeping 10 things, the probability I keep it is going to be 10 divided by 200, which is 5%. So 0.05% of the time, I keep the or 0.05 probability, I keep the 200th thing in the stream if I'm keeping a random sample of size 10.
Right. So as this probability decreases, it decreases the probability that we do a sample.
That's right. Yep. Okay.
So how dependent on this is like you have and values are values same.
Yeah, it cares about individual items. It doesn't look at the value at all.
Okay.
So it's oblivious to the values. And at the end of the stream, each item is in the reservoir with probability K over N if I've seen N things in the stream. Okay, and you can prove this. It's a few lines of calculation. I'm not going to do it, but that you can prove it inductively going, you can say, look at the J thing that I'm currently seeing, and I want at the end of this step for the J thing, I want to keep it with probably K over J. Correct? That's the right probability to keep it. And then I have to argue that all the previous things are now kept with that probability. They used to be kept with probability k over j minus 1. And then I throw them out with some probability. You can write this down, and you show that that is updated to k over j after this.
So the sample would do a good job.
Great, yes. So this would, a random sample, this might do a good job of capturing the mean. Is a random sample a good approximation of the mean? So maybe it depends on it. This is a, yeah, if you, we didn't talk about this in this class. If you took 3190, there were some concentration bounds that you may have seen. If you know the mean and the variance, for instance, you can use a Chebyshev bound to say that if the variance is bounded, then I have a good approximation of the mean. Or if I know that the values are between, say, 0 and 1, I can apply a Chernoff-Hofting bound and get an even better concentration. Okay, yeah. So the random sample will give me an approximation of a lot of different questions, including the mean, assuming the spread or the variance some way is controlled. Yeah, great. So this is kind of a very useful summary that has like, it's like the jack of all trades and usually like the master of none, right? So the mean I could do better. This required k to be larger and larger to get a better and better approximation of the mean, where if I used this algorithm here, I did it in constant space. Okay, so this was better for doing the mean, but the reservoir sampling can also give me the mean of the data, assuming that the spread is bound. All right, great. This is probably, yeah. Yeah, these are two of the most useful algorithms. Like, I guess as we go on, are going to become less and less useful, but don't leave middle of the class. Okay, so the next thing we'll talk about is what you'll do on your homework. So definitely don't leave yet. Okay. Okay. I want to talk about a slightly different setting now, where instead of thinking about real values, we're going to say that, again, I have a stream, A equals A1, A2, up to AI, AN, I guess. Okay, and now instead of saying each of the AIs was a real value, we're going to say each AI is going to be in a large set. Okay, so there's a large set, a discrete space of size M. Okay, remember we talked about this sort of model in the early part of the semester. Think of the space of M is going to be IP addresses. Right, so if you're sitting on a router, keeping track of something about the IP addresses, either they're sending to or from, seems like something that would make sense to keep track of. It could be, this could be the all the K grams that you're considering you witness in the English language as you're scanning text, right? Maybe remember there were maybe 100,000 words, and if K is 3, I could maybe potentially see 100,000 to the third different K grams I might see. Okay, and I want to somehow keep track of the set of things. Okay, and I'm particularly interested if anything occurs a lot. Okay, if I'm thinking about the IP addresses, one of the places this was developed was for routers. It developed a lot at AT&T. So if you've heard of Bell Labs, this was a really important research lab where like k-means clustering, or the Lloyd's algorithm for k-means clustering was invented. A lot of information theory grew out of there. I think maybe kind of was the Unix operating system may have come out of there. This was kind of really important research lab. They were AT&T, which used to be a monopoly of the phone system. And so they were tracking, they were the pre-internet notion of internet. They were sending signals on the phone lines, and when they broke this up, it's led to being able to democratize stuff and the open internet we have today. But they were very interested in this. And so they were wondering, I'm sending packets on the internet or through a phone line, and there's a location like an IP address. And I'm worried that someone's trying to cause a distributed denial of service attack on one of the IP addresses. Okay, so how does this work? A lot of different computers which have like spam malware running on them, they activate them and they have them all send messages to one IP address, and that computer then gets overloaded. Too much information is coming in, it can't get the information it needs, the computer crashes. Okay, and they want to be able to sit on a router and monitor whether one IP address is getting lots and lots of packets before they get there. Okay, they want to notice this somewhere in the router network, that is the internet or was the phone system, to monitor whether there's too many stuff going to one of the IP addresses, and then they will try and detect it and stop it and do, something like that. Okay, so they want to find if there's any packet or IP address which is being hit too often. Okay. Other things in like the K-grams. What are interesting K-grams? Which are ones that actually are occurring a lot, right? And maybe occur a lot against some known distribution of things, right? We want to do some anomaly detection against some baseline estimate of what are the K-grams. I've maintained a distribution of them, and then I want to compare against what I'm seeing in this part of the documents. Is there some other word or K-gram which is very popular? So there were these early things of meme detection. Now you don't need to detect memes because you all know about them, but they used to be before they were like dance videos and stuff. There was just like strings of text would identify a meme, and they wanted to detect it because it was an unusual K-gram. Okay, so these are kind of the applications here. I have all these things, and the problem is that now both M and N are too big. Okay, so I can't keep a counter for every IP address. I can't keep a counter for every K-gram. I can't possibly do this, right? The same way on a router, I can't keep all the packets or all the information of all the packets. So I somehow want to find the large ones without keeping a counter for everything. Okay, so what I can store is going to be, there are things that I can store. I can basically store a label, okay, J in the set M, right? This would be like one IP address, and the label is log of M bits. Okay, I can't store M things, but I can store log of M things, and I can represent it with log of M bits, and I can have a counter, which will be a value J in values up to N, right? I can think of counting how many things I've seen. Maybe I'll call this I, right? A counter, and this will be log of N bits, right? And this is also something makes sense to store and keep track. These are feasible things to do, okay? And what I would like to keep track of is the large things. What I need to know are, I'll call the frequency, okay? The frequency f of j for j in the space of, say, all IP addresses or all of the K-grams. I want to maintain, which is the number of AI in the set A, such that AI is equal to j. Okay, so I want to know the count of the jth IP address. How many times did I see this? Okay, I want to maintain this, and in particular, what would be called the heavy hitters. Okay, a heavy hitter would be a j such that fj is larger than phi of n. So think of phi as, say, 0.1. So it'd be like is larger than 10% of the data. More than 10% of the data, maybe it's 0.01. Well, is bigger than 1% of the data, or maybe, 1 out of 1,000. Think of, depending on the scale you're thinking about, bigger than some fraction of the data. A denial of service attack might be maybe 0.02 or something. That would, they really send a lot of traffic at once across all of the routers in some vicinity of the computer that's being so targeted. Okay, but I'm often allowed, but this turns out, understanding this threshold exactly turns out to be hard. So I'm gonna say it's okay if I might accidentally return it if fj is greater than phi of n minus epsilon of n. Okay, and we're gonna think of epsilon as 0.01. Okay, think of it as maybe something here. So if I have these values, I say it's a heavy hitter. If it's bigger than 10%, I should return all heavy hitters, but I don't want to miss anything. I'm allowed some approximation. So if it's bigger than 9% of things, it's okay if I accidentally report it. This might be a false positive, but it's still pretty significant. Okay, so these numbers, it's definitely return it if it's bigger than 10%, maybe return it if it's bigger than 9%. Don't return it if it's less than 9%. Okay, and I can change these parameters, but these are good things to think about for how stuff's going to work. Okay, and so I can solve this. What we're ultimately going to do, and I'm going to come back to this again, but we're going to get an approximate frequency we'll call f hat of j, and we'll have the property that f hat of j, or fj minus f hat of j, is going to be less than epsilon n. Okay, so let's say that I'm going to be able to return an approximate frequency, put the hat on it, means it's approximate. It'll be off by epsilon n, which is say 1%. And if then I can look at the approximate frequencies and return any approximate frequency bigger than 10%, it will satisfy this. Okay, so we'll come back to this problem. Okay, how do we solve this? I'm going to start with a simpler problem. Okay. Okay, and now again, we're going to have, and this is a simpler problem called majority. Again, we're going to have A1 up to AN. Okay, and each AI is going to be in M. Okay, and what I want to have is that if there is some Fj greater, strictly greater than M over 2, then I'm going to output J. Else, then I can output, so I can output anything, any J prime in M. Okay, so the idea is that all the things I'm seeing are still voting. Okay, and I want to know if there was something that was a majority of the votes. I can have a lot of IP addresses, but if something is a majority of them, more than half, right, a strict majority, then I need to report it. If there wasn't a majority, I can return anything. Okay, so this is the problem, and I'm going to solve this with one counter and one label. All right, so this is some J in M, and this is some value in N. Okay, so I'm going to do one counter and one label. Those are the two things I have space to keep. How am I going to solve this problem? Okay, we'll call this label L, and this counter C. Okay, so what's the thing to do? Well, let's think of the cases. If my if AJ is equal to my label, right? If the thing I see is equal to the label, okay, so what else? You know, the options are AJ is equal to the label or it's not equal to the label. That's basically all I can tell with one label. Okay, so what should I do if it's equal to the label? Okay, I'm going to increment the counter, right? If it's equal to the label, then I'll say my counter is going to be counter plus 1. Okay, makes sense? Hoping, okay, if it's equal to the label, then maybe I'm counting the thing I'm seeing, so I should increment the counter. If it's not equal to the label, what should I do? Great, okay, if it's not equal to the label, I should decrement the counter, -1. Okay. To do something else here, and this is kind of where the magic happens. Else, this is part of the else statement. If now C is less than 0, I'm going to set the label equals to AI. And I'm going to set the counter equals to 1. See at least one of those things. Okay, so this is the algorithm. Okay, so I just have one counter. And if I see something, I'm going to increment it. If I see what I'm keeping count of, I'm going to increment it. If I see something else, I'm going to decrement it. Okay? And if it goes below 0, well, then I know whatever I was keeping count of, I saw a lot of something else, right? And that counter was decremented below 0, so I saw more of, since I started keeping track of that, I saw more of something else than I saw of that counter. So I'm gonna, well, change the label. Change the label to what I currently see. I know I've seen at least one of these. So I'm gonna set the counter to 1. Okay, and maybe I start by assigning something to the first step, I assign it to the first label, and I set the counter to 1, or you can initialize this some symbol. Okay, and so I can argue that this satisfies this majority problem. Okay, if a counter, basically, I can think of keeping track of 2 labels, L1 and L2, and I'm going to have a bar for how many are in L1, and then how many is everything else. And you can argue that if label 1 is the thing that is the majority, that this bar will always, this bar will always be bigger than the bar of everything else. And so these are kind of all the subtractions, or I may have accidentally subtracted something from here because I was using the wrong label. And so I can argue, and if this is always bigger, then there'll be more counts with this label than there will be everything else. I'm not gonna try and, the proof isn't hard, but you got to get some conditions right. So I'm not gonna go through it, but this is a sufficient algorithm for this problem. Again, a very simple thing with one counter and one label. Yeah.
If there is not a very common list, all this algorithm is returned some.
I don't have any guarantees. If I don't have a majority, I don't have any control over what I will return.
Right.
Yeah. So this is kind of a weird weakness of this definition, but this is what I can guarantee. The statement up here. So if this condition is not true, then I'll be in else. In the else condition, I can output anything.
Right. I'm just trying to, like, this algorithm, if we don't know the input, we can't have confidence that the output is the
Right. Yep. Okay, I will fix that next. Okay, good. So this was kind of this was a warm up. Okay, I wrote the algorithm out here in case you want to go through it. Okay, now I want to go back to this frequency approximation problem. Okay, let's go back to frequency approximation. Okay, and what I'm going to talk about is what's called the Misra-Gries algorithm. Okay, and this was from 1982, and then it was rediscovered by 3 separate research groups, basically in around 2005. Okay, so 3 different groups basically came up with the same algorithm, up to some very minor changes. It took 10 years, maybe it was 10 years later before we realized they were all the same algorithm. Okay, and this is going to, the goal is going to be to, for all j in M, a value fj such that fj hat, sorry, will satisfy that it's going to be less than fj and greater than fj, the true value, the true frequency, minus n over k. K is going to be a parameter. Okay, again, like the number of samples. Actually, if I can approximate this actually using k equals 1 over epsilon squared samples, I can get with some with probability, constant probability, I can get all of these within a 1 plus epsilon. With I can make that a minus 1 plus or minus epsilon error on either side with k equals 1 over epsilon squared samples. But I'm going to do it with basically k equals 1 over epsilon kind of counters and labels. So I'm going to use k minus 1 counters and k minus 1, so k minus 1 labels. Okay, and we're going to set k equals to 1 over epsilon, right? So this, if k equals 1 over epsilon, then n over k equals epsilon n, right? So that means my estimate will always be less than the true value, but not too much less, not more than epsilon n less. And so I can use this to find these heavy hitter questions with this value of epsilon. So if this is 1%, 0.01, 1 over epsilon is 100. Okay, so I keep 100 counters or labels, and I keep track of all frequencies within 1% accuracy. Okay. Okay, and so this will be the approximate frequency. Okay. Okay, so our data structure again is going to be these labels L1, L2 up to Lk minus 1. And I'm going to have with these some counters, C1, C2 up to K minus 1. Okay, and then, so it's going to look like the majority algorithm, but I'm going to get this much stronger guarantee. Instead of using 1 counter and label, I'm going to use K minus 1 of them. Okay, so let's kind of start writing out the algorithm here. And we'll think of it as a for loop for AI and A. So this is how you would implement this. Okay. And we'll call this set L. Okay, so if AI is in the set L, so it's one of the labels, right? And let's say AI is equal to label J, okay? Then what I'm going to do, I'm going to increment counter J equals counter J plus 1. I'm going to add 1 to this counter, right? So if one of the labels matches, that means this is what I'm keeping count of. I'm going to increment this counter. Okay. Else, okay, if AI is not in L, okay, now I have to make a choice. Okay. So now there are two things that can happen. One is if some Cj is less than or equal to 0, then what I can do, well, then I can set in this case, I'm going to set label J equals to AI, and I'm going to set counter J equals to 1. Okay, so if I had basically a counter that was set to 0 or initialized to empty somehow, okay, I can I can use that as the new label, and I can set the counter to 1. Okay, but what if I don't have any labels that aren't being used already? Okay. Okay, else, there's one more thing, and I'm running out of room at the bottom here. So, okay, what if, and this is the case that no labels unused. Right? So what should I do if no of the labels are unused? Yep. Pick the label with the lowest count and get rid of it. So what do you mean by get rid of it? And replace it with the current item I'm on. And what should I do with the count? Okay, so if you keep the count of the old label and replace it but swap the label, this is called the space saving algorithm. Okay, and this actually works, and turns out to be isometric to what we're gonna do, but it's a little bit more complicated to understand. Okay, so you're close, but there's something else you can do, which is maybe less intuitive. Okay, what's another thing you can do?
Decrease the counter.
Decrease what counter?
For all the counters.
Decrease all the counters, yes. So in this case, I'm going to decrease all counters by 1. So for all j, Cj equals Cj minus 1. Okay, so I'm going to decrement all of the counters. Okay, so it seems weird I would decrement all of the counters, but then, so it's going to kind of work kind of like the majority algorithm, but I want to decrease all of the counters now, not just the smallest one. If I just decrease the smallest one, I can never kind of fix if I made a bad decision and a count got too high. So I need to decrease all of them. Okay. Okay, let's look at, okay, so I've got the algorithm here, and let me try and draw a picture to go along with it now. I think this is, let's see, I've got counter array, I've got my location or label array, and initialize them, yeah, and then I have this for loop of up to n, okay, 1 to n, and I've if it matches a label, I increment the counter, right? If it matches the label, I increment the counter. If it doesn't, and some counter is equal to 0, well, then I can replace it. I take it over and I set the counter to 1. Otherwise, for all of the counters, I decrease them by 1. Okay, so this is the same algorithm, but written more clearly than I tried to squeeze in the bottom of the slide. Okay, and let's just kind of go through, draw a pictorial example. Imagine I have label 1, label 2, label 3, label 4, label 5, and I'm going to have these different kind of counters, which I'll think of as bars, right? And again, the height of it is going to be the number of things I've stored in the count. Yes.
If there are T-1 labels, isn't this just keeping track of every label?
Yeah, so so the total number of IP addresses is M, right? And M is so huge. I can't keep track of all IP addresses. I'm keeping track of like 100 IP addresses, right? There's something like some billions of IP addresses, right? I can't keep track of all of them. I'm just keeping track of 100 of them. And I'm going to guarantee that every counter will be within 1% error, which is pretty cool, right? So if I wanted 1/10 of 1% error, I'd keep track of 1,000. That's so manageable. If I had to do this with random sampling, I could randomly sample the stuff with reservoir sampling, and everything I had would be a good estimate. But in order to get 1% error, I would need 10,000 counters. To get 1/10 of 1% error, I would need 1,000,000 counters. So I'm saving a huge kind of space by using this algorithm instead.
So is the error amount of occurrences, or is it in the
For each counter, I individually have this guarantee for each frequency. Okay, yeah, there's something I didn't ask you about. I said this holds for all frequencies. What if J is not one of my labels? How do I return an estimate F hat J? If it's the label, I just use the counter associated with the label, right? If it's not one of the labels, what should I return? Should I return 5? What's a good answer to return? The average. Turns out you can return 0. Okay, I return 0, and I'm allowed to undercount. Okay, is it possible that I can get it accurate? I've only stored 100 counters out of 1 billion different IP addresses. Can I possibly get 1% error on all of them? Well, how many different IP addresses can have 1% of the data? Only 100 can have 1% of the data. If I have 100 things with 1% of the data, that's all the data. So I can't have more than 100 things that have 1% of the data. So most of them are going to be really small. And so most of them I can return 0. And if I just care about the really heavy things, that's fine. Those are not, the ones I return 0 are not the heavy hitters. Okay? Okay. So, yeah, so if I see something with label 4, right, then I'm incrementing this counter. I'm adding something here. But then if I see something with none of the labels, right, then I could think of chopping off the top. So I remove this one. So I reduce the layer on all of these things. Okay, yeah. Oh, if you find a matching label, you don't do the decrement. Okay. Because I know that I've seen something and I've seen it again, so I should increase the counter. I only introduce error when I've decremented a label. Each of the counters, I know it has at least that many things in it, right? If I have a label 1 and this is IP address of my computer and I see a packet going to it, I know that I saw that packet. That is a better count. Each of the counts corresponds with an actual event. So I don't want to decrement. That every time I decrement, I'm introducing error. Okay? So what is the max amount of error I can, if every frequency item, every frequency estimate it's never an overcount because I only increment if I see something that matches. And I only get error if I do one of the decrements. Okay, how many times? So the error is the number of times I've I've done a decrement, right? The number of times I've decremented stuff. How many times can I decrement, do this decrement operation where I reduce one from all the counters? If I have 10 of these things, how many times? So how many total, so decrements? Okay, we'll finish up after this.
Would it be minus?
Not n minus k, but n, the answer is n divided by k, because every time I do it, I have k minus 1 counters and the thing I'm currently seeing. So every time I do a decrement, I'm removing k things from my total count. So I have n things total, and I remove k things each time. This is the number of times I can do it. Okay? If I can only do it that many times, then the amount of error I have in any frequency is at most n over k. And what did I claim the error was going to be? I claimed the error was going to be n over k. That's the number of decrements. If I set k equals to 1 over epsilon, 100 for 1% error, then I get this error guarantee. Okay, so that's the proof. That's the proof that this works. Okay, and so it's a generalization of that majority algorithm, but if I keep more counters, I get this thing. This is optimal. I can't do better than this. This is the best possible thing I can do, and I save from this, I have a square root of the size I would need to get the same or even worse error bounds if I used a random sample instead. It's a much more compact sketch, streaming sketch here. So cool. Okay, we'll stop here. And then we'll talk a little bit more streaming algorithms next week on Monday.